All right, everyone, let us dive right on in to learning about how to calculate the mean and the standard deviation for a binomial distribution. Now, both these formulas are on your exam formula sheet. Directly underneath the formulas for mean and standard deviation, or I should say mean and variance of just a normal nothing special probability distribution. This only works for binomial. And the way you'll know that it only works for binomial is binomial is the only one that has n and p, right? Where n is the number of trials and p is the probability of success. You can still use the other formulas to calculate mean and standard deviation through the variance. However, it will take you much longer, and this is so much simpler and actually shows that you know that it's binomial. So please use these to find the mean and standard deviation. So here's our first example. When rolling 2 dice, the probability of rolling doubles is 1/6. Suppose that a game player rolls the dice 4 times, hoping to roll doubles. What are the mean and standard deviation of this distribution? So n here is 4, p is 1/6, so 4 times 1/6 is 4/6, which is 2/3, which is 0.6 repeating. The standard deviation, square root of n times p times 1 minus p, so 4 times 1/6 times 5/6. Is the square root of 2036, which is 0.745. See how simple that was? No crazy calculations to do. When we have a binomial distribution, we can also describe it just like we do any other distribution. We can talk about its shape, its center, and its spread. So what you see below is a probability distribution for a binomial situation. X represents the number of children with type O blood in a family with 5 children. You see the possible outcomes, number of successes, and the probability of each one, okay? This came from obviously more information, but it's a binomial distribution. Let's go through and describe our distribution. In this, the shape of the probability distribution is skewed to the right. It is more likely to have 0, 1, or 2 children with type O blood than a larger value. The center, the median number of children with type O blood is 1. The mean is 1.25, which you can calculate. The spread, the variance is 0.9375, and the standard deviation is 0.96. This example came from the book if you want to see where those numbers came from as far as their calculations are concerned. All right, let's look at another example. The makers of a Diet Cola claim that its taste is indistinguishable from the full-calorie version of the same cola. Samples were prepared of each type of soda in identical cups. Volunteers tasted each cola in a random order and tried to identify the regular and the diet. Overall, 23 of 30 subjects were correct. If we assume that the volunteers couldn't really tell the difference, then each one was guessing with a 1/2 chance of being correct. Let's let X represent the number of volunteers who correctly identify the colas. First, we're going to explain why this is a binomial random variable. Then we're going to calculate the mean and the standard deviation, interpreting each one in context. And then we're going to see if this basically gives us any evidence that they can taste the difference. So explaining why it's a random variable, a binomial random variable. The chance process is each volunteer guessing which sample is the Diet Cola. So let's go through our bins. B stands for binary. And yes, this is binary. Either the guesses are correct or they are incorrect. I stands for independent. And again, yes, the results of one volunteer's guess should have no effect on the results of other volunteers' guesses. Is this being done for a set number of trials? Yes, there were 30 subjects, so 30 trials. And does the probability of success stay the same? Yeah, if they're truly guessing, you have a 50% chance or a 1/2 chance of guessing correctly. Since X is counting the number of successful guesses, X would be considered a binomial random variable. Now we want to find the mean and the standard deviation of X, interpret each value in context. So mean, you calculate n times p. N was our 30 subjects or our 30 trials times the probability of success 0.5, which gives us 15. Standard deviation is there, and you get 2.74. Now, how do we interpret this value in context? If this experiment were repeated many times and the volunteers were in fact randomly guessing, the average number of correct guesses would be about 15, and the number of correct guesses would vary from 15 by about 2.74 on average. So that's kind of a combination combining the interpretation of both mean and standard deviation together. Of the 30 volunteers, 23 were in fact correct. Does this give convincing evidence that the volunteers can taste the difference between regular and Diet Cola? Let's do the calculations. What's the probability that 23 or more were correct? Well, to figure out the probability of 23 or more being correct, let's find the complement, because we can use our calculator that way, the probability of 1 minus 22 or less. So I can use my binomial CDF of 30.5 and 22, where n is 30, p is 0.5, and x is 22. Remember, you have to identify these. And that ends up giving us a probability of, ooh, that's pretty small, 0.0026. So there is a very small chance that there would be 23 or more correct guesses if the volunteers couldn't tell the difference. So because it's so small, we then have convincing evidence that the volunteers can, in fact, taste the difference. This is going to be something we do a lot of in the second semester, using probability to help us figure out if something is convincing or not. I'm going to stop this video here, and the next video is going to be all about our next probability distribution, which is called geometrics, just so they're not so long. So next video, watch it. It goes with this one, but I just don't want them to be super long. So stay tuned for the next video.